A tessellation of a flat surface is the tiling of a plane using one or more geometric shapes, called tiles, with no overlaps and no gaps. In mathematics, tessellations can be generalized to higher dimensions and a variety of geometries. A periodic tiling has a repeating pattern. Some special kinds include regular tilings with regular polygonal tiles all of the same shape, and semi-regular tilings with regular tiles of more than one shape and with every corner identically arranged. The patterns formed by periodic tilings can be categorized into 17 wallpaper groups. A tiling that lacks a repeating pattern is called non-periodic. An aperiodic tiling uses a small set of tile shapes that cannot form a repeating pattern. In the geometry of higher dimensions, a space-filling or honeycomb is also called a tessellation of space. A real physical tessellation is a tiling made of materials such as cemented ceramic squares or hexagons. Such tilings may be decorative patterns, or may have functions such as providing durable and water-resistant pavement, floor or wall coverings. Historically, tessellations were used in ancient Roman and Islamic art such as in the decorative tiling of the Alhambra Palace. In the 20th century, the work of M.C. Escher often made use of tessellations, both in ordinary Euclidean geometry and in hyperbolic geometry, for artistic effect. Tessellations are sometimes employed for decorative effect in quilting. Tessellations form a class of patterns in nature, for example in the arrays of hexagonal cells found in honeycombs. History. Tessellations were used by the Sumerians in building wall decorations formed by patterns of clay tiles. Decorative mosaic tilings made of small squared blocks called tesserae were widely employed in classical antiquity, sometimes displaying geometric patterns. In 1619, Johannes Kepler made an early documented study of tessellations. He wrote about regular and semi-regular tessellations in his Harmonices Mundi. He was possibly the first to explore and to explain the hexagonal structures of honeycomb and snowflakes. Some 200 years later, in 1891, the Russian crystallographer Yevgraf Fyodorov proved that every periodic tiling of the plane features one of 17 different groups of isometries. Fyodorov's work marked the unofficial beginning of the mathematical study of tessellations. Other prominent contributors include Shubanov and Belov, and Heinrich Heesch and Otto Kienzl. Etymology in Latin. Tessellate is a small cubical piece of clay, stone or glass used to make mosaics. The word tessellate means small square. It corresponds with the everyday term tiling, which refers to applications of tessellations, often made of glazed clay. Overview. Tessellation, or tiling in two dimensions, is a topic in geometry that studies how shapes, known as tiles, can be arranged to fill a plane without any gaps, according to a given set of rules. These rules can be varied. Common ones are that there must be no gaps between tiles, and that no corner of one tile can lie along the edge of another. The tessellations created by bonded brickwork do not obey this rule. Among those that do, a regular tessellation has both identical regular tiles and identical regular corners or vertices, having the same angle between adjacent edges for every tile. There are only three shapes that can form such regular tessellations: the equilateral triangle, square, and regular hexagon. Any one of these three shapes can be duplicated infinitely to fill a plane with no gaps. Many other types of tessellation are possible under different constraints. For example, there are 8 types of semi-regular tessellation, made with more than one kind of regular polygon but still having the same arrangement of polygons at every corner. Irregular tessellations can also be made from other shapes such as pentagons, polyominoes, and in fact almost any kind of geometric shape. The artist M.C. Escher is famous for making tessellations with irregular interlocking tiles, shaped like animals and other natural objects. If suitable contrasting colors are chosen for the tiles of differing shape, striking patterns are formed. and these can be used to decorate physical surfaces such as church floors. More formally, a tessellation or tiling is a cover of the Euclidean plane by a countable number of closed sets, called tiles, such that the tiles intersect only on the boundaries. These tiles may be polygons or any other shapes. Many tessellations are formed from a finite number of prototiles in which all tiles in the tessellation are congruent to the given prototiles. If a geometric shape can be used as a prototile to create a tessellation, the shape is said to tessellate or to tile the plane. The Conway criterion is a sufficient but not necessary set of rules for deciding if a given shape tiles the plane periodically without reflections. Some tiles fail the criterion but still tile the plane. No general rule has been found for determining if a given shape can tile the plane or not, which means there are many unsolved problems concerning tessellations. For example, the types of convex pentagon that can tile the plane remains an unsolved problem. Mathematically, tessellations can be extended to spaces other than the Euclidean plane. The Swiss geometer Ludwig Schläfli pioneered this by defining polyschemes, which mathematicians nowadays call polytopes. These are the analogues to polygons and polyhedra in spaces with more dimensions. He further defined the Schläfli symbol notation to make it easy to describe polytopes. For example, the Schläfli symbol for an equilateral triangle is 3, while that for a square is 4. The Schläfli notation makes it possible to describe tilings compactly. For example, a tiling of regular hexagons has 3 six-sided polygons at each vertex, so its Schläfli symbol is 6, 3. Other methods also exist for describing polygonal tilings. When the tessellation is made of regular polygons, the most common notation is the vertex configuration, which is simply a list of the number of sides of the polygons around a vertex. The square tiling has a vertex configuration of 4.4.4.4, or 44. The tiling of regular hexagons is noted 6.6.6, or 63. In mathematics, Introduction to Tessellations, mathematicians use some technical terms when discussing tilings. An edge is the intersection between two bordering tiles. It is often a straight line. A vertex is the point of intersection of 3 or more bordering tiles. Using these terms, an isogonal or vertex transitive tiling is a tiling where every vertex point is identical, that is, the arrangement of polygons about each vertex is the same. The fundamental region is a shape such as a rectangle that is repeated to form the tessellation. For example, a regular tessellation of the plane with squares has a meeting of 4 squares at every vertex. The sides of the polygons are not necessarily identical to the edges of the tiles. An edge-to-edge tiling is any polygonal tessellation where adjacent tiles only share one full side, i.e., no tile shares a partial side or more than one side with any other tile. In an edge-to-edge tiling, the sides of the polygons in the edges of the tiles are the same. The familiar brick wall tiling is not edge-to-edge because the long side of each rectangular brick is shared with 2 bordering bricks. A normal tiling is a tessellation for which every tile is topologically equivalent to a disk. The intersection of any 2 tiles is a single connected set or the empty set, and all tiles are uniformly bounded. This means that a single circumscribing radius and a single inscribing radius can be used for all the tiles in the whole tiling. The condition disallows tiles that are pathologically long or thin. A monohedral tiling is a tessellation in which all tiles are congruent. It has only one prototile. A particularly interesting type of monohedral tessellation is the spiral monohedral tiling. The first spiral monohedral tiling was discovered by Heinz Voderberg in 1936. The Voderberg tiling has a unit tile that is a non-convex enneagon. The Hirschhorn tiling, published by Michael D. Hirschhorn and D. C. Hunt in 1985, is a pentagon tiling using irregular pentagons. Regular pentagons cannot tile the Euclidean plane, as the internal angle of a regular pentagon, 3 pi 5, is not a divisor of 2 pi. An isohedral tiling is a special variation of a monohedral tiling in which all tiles belong to the same transitivity class, that is, all tiles are transforms of the same prototile under the symmetry group of the tiling. If a prototile admits a tiling, but no such tiling is isohedral, then the prototile is called anisohedral and forms anisohedral tilings. A regular tessellation is a highly symmetric, edge-to-edge tiling made up of regular polygons, all of the same shape. There are only 3 regular tessellations: those made up of equilateral triangles, squares, or regular hexagons. All 3 of these tilings are isogonal and monohedral. A semi-regular tessellation uses more than one type of regular polygon in an isogonal arrangement. There are 8 semi-regular tilings. These can be described by their vertex configuration. For example, a semi-regular tiling using squares and regular octagons has the vertex configuration 4.82. Many non-edge-to-edge tilings of the Euclidean plane are possible, including the family of Pythagorean tilings. Tessellations that use 2 sizes of square, each square touching 4 squares of the other size. Wallpaper groups tilings with translational symmetry in 2 independent directions can be categorized by wallpaper groups, of which 17 exist. It has been claimed that all 17 of these groups are represented in the Alhambra Palace in Granada, Spain. Though this is disputed, the variety and sophistication of the Alhambra tilings have surprised modern researchers. Of the 3 regular tilings, 2 are in the P6 meters wallpaper group and 1 is in P4 meters. Tilings in 2D with translational symmetry in just one direction can be categorized by the 7 frieze groups describing the possible frieze patterns. Orbifold notation can be used to describe wallpaper groups of the Euclidean plane. Aperiodic tilings, Penrose tilings, which use 2 different quadrilaterals, are the best-known example of tiles that forcibly create non-periodic patterns. They belong to a general class of aperiodic tilings, which use tiles that cannot tessellate periodically. The recursive process of substitution tiling is a method of generating aperiodic tilings. One class that can be generated in this way is the Wahida tiles. These tilings have surprising self-replicating properties. Pinwheel tilings are non-periodic. Using a Wahida tile construction, the tiles appear in infinitely many orientations. It might be thought that a non-periodic pattern would be entirely without symmetry, but this is not so. Aperiodic tilings, while lacking in translational symmetry, do have symmetries of other types. By infinite repetition of any bounded patch of the tiling and in certain finite groups of rotations or reflections of those patches. A substitution rule, such as can be used to generate some Penrose patterns using assemblies of tiles called ROM, illustrates scaling symmetry. A Fibonacci word can be used to build an aperiodic tiling, and to study quasi-crystals, which are structures with aperiodic order. Wang tiles are squares colored on each edge, and placed so that abutting edges of adjacent tiles have the same color, hence they are sometimes called Huang dominoes. A suitable set of Huang dominoes can tile the plane, but only aperiodically. This is known because any Turing machine can be represented as a set of Huang dominoes that tile the plane if and only if the Turing machine does not halt. Since the halting problem is undecidable, the problem of deciding whether a Huang domino set can tile the plane is also undecidable. Truchet tiles are square tiles decorated with patterns so they do not have rotational symmetry. In 1704, Sébastien Truchet used a square tile split into 2 triangles of contrasting colors. These can tile the plane either periodically or randomly. Tessellations and color. Sometimes the color of a tile is understood as part of the tiling. At other times arbitrary colors may be applied later, when discussing a tiling that is displayed in colors. To avoid ambiguity, one needs to specify whether the colors are part of the tiling or just part of its illustration. This affects whether tiles with the same shape but different colors are considered identical, which in turn affects questions of symmetry. The four-color theorem states that for every tessellation of a normal Euclidean plane, with a set of four available colors, each tile can be colored in one color such that no tiles of equal color meet at a curve of positive length. The coloring guaranteed by the four-color theorem does not generally respect the symmetries of the tessellation. To produce a coloring which does, it is necessary to treat the colors as part of the tessellation. Here, as many as 7 colors may be needed, as in the picture at right. Tessellations with polygons next to the various tilings by regular polygons. Tilings by other polygons have also been studied. Any triangle or quadrilateral can be used as a prototile to form a monohedral tessellation, often in more than one way. Copies of an arbitrary quadrilateral can form a tessellation with translational symmetry and two-fold rotational symmetry with centers at the midpoints of all sides. For an asymmetric quadrilateral, this tiling belongs to wallpaper group P2. As fundamental domain we have the quadrilateral. Equivalently, we can construct a parallelogram subtended by a minimal set of translation vectors, starting from a rotational center. We can divide this by one diagonal, and take 1/2 as fundamental domain. Such a triangle has the same area as the quadrilateral and can be constructed from it by cutting and pasting. If only one shape of tile is allowed, tilings exists with convex n-gons for n equal to 3, 4, 5 and 6. For n equals 5, see pentagonal tiling, and for n equals 6, see hexagonal tiling. For results on tiling the plane with polyominoes, see polyomino uses of polyominoes. Voronoi tilings. Voronoi or Dirichlet tilings are tessellations where each tile is defined as the set of points closest to one of the points in a discrete set of defining points. The Voronoi cell for each defining point is a convex polygon. The Delaunay triangulation is a tessellation that is the dual graph of a Voronoi tessellation. Delaunay triangulations are useful in numerical simulation, in part because among all possible triangulations of the defining points, Delaunay triangulations maximize the minimum of the angles formed by the edges. Voronoi tilings with randomly placed points can be used to construct random tilings of the plane. Tessellations in higher dimensions. Tessellation can be extended to 3 dimensions. Certain polyhedra can be stacked in a regular crystal pattern to fill 3-dimensional space, including the cube, the rhombic dodecahedron, and the truncated octahedron. Naturally occurring rhombic dodecahedra are found as crystals of andradite and fluorite. A Schwarz triangle is a spherical triangle that can be used to tile a sphere. Tessellations in 3 or more dimensions are called honeycombs. In 3 dimensions there is just one regular honeycomb, which has 8 cubes at each polyhedron vertex. Similarly, in 3 dimensions there is just one quasi-regular honeycomb, which has 8 tetrahedra and 6 octahedra at each polyhedron vertex. However, there are many possible semi-regular honeycombs in 3 dimensions. Uniform polyhedra can be constructed using the Wythoff construction. The Schmidt-Conway biprism is a convex polyhedron with the property of tiling space only aperiodically. Tessellations in non-Euclidean geometries. It is possible to tessellate in non-Euclidean geometries such as hyperbolic geometry. A uniform tiling in the hyperbolic plane is an edge-to-edge filling of the hyperbolic plane, with regular polygons as faces. These are vertex transitive and isogonal. A uniform honeycomb in hyperbolic space is a uniform tessellation of uniform polyhedral cells. In 3-dimensional hyperbolic space there are 9 Coxeter group families of compact convex uniform honeycombs, generated as Wythoff constructions, and represented by permutations of rings of the Coxeter diagrams for each family. In art, in architecture, tessellations have been used to create decorative motifs since ancient times. Mosaic tilings often had geometric patterns. Later civilizations also used larger tiles, either plain or individually decorated. Some of the most decorative were the Moorish wall tilings of Islamic architecture, using Giri and Zellige tiles in buildings such as the Alhambra and La Mezquita. Tessellations frequently appeared in the graphic art of M.C. Escher. He was inspired by the Moorish use of symmetry in places such as the Alhambra when he visited Spain in 1936. Escher made 4 circle limit drawings of tilings that use hyperbolic geometry. For his woodcut circle limit IV, Escher prepared a pencil and ink study showing the required geometry. Escher explained that no single component of all the series, which from infinitely far away rise like rockets perpendicularly from the limit and are at last lost in it, ever reaches the boundary line. Tessellated designs often appear on textiles, whether woven, stitched in or printed. Tessellation patterns have been used to design interlocking motifs of patch shapes in quilts. Tessellations are also a main genre in origami, where pleats are used to connect molecules such as twist folds together in a repeating fashion. In manufacturing, tessellation is used in manufacturing industry to reduce the wastage of materials such as sheet metal when cutting out shapes for objects like car doors or drinks cans.